Hello, world. In 2021, we leave no one behind.
Hello and welcome to the VoiceOver for VoiceOver. For almost all of the people with hearing and speech impediments in the US, American Sign Language is the only way to connect to the rest of the world. However, even in 2021, they feel disconnected, particularly so in schools, colleges, and in workplaces. Let's look at some stats. So the National Deaf Center reports that almost 54% of the deaf students do not participate in any student activities, and more than half do not even have a way to give formal feedback to their service providers. And now COVID has only made it worse for them, with more than 74% reporting that online learning is more difficult and that universities are going as far as even denying them interpreters due to their contractual obligations. In almost every sphere of their lives, they feel left out and forgotten. There exists a huge communication barrier which everyone wants to overcome. And with VoiceOver, we aim to do just that. VoiceOver uses computer vision and machine learning to convert ASL to speech to help ASL users connect better in classrooms, workspaces, and real life, so that we can truly and proudly say that we are leaving no one behind.
So let's talk about how an actual user would use VoiceOver. One way to do this is as an integration with existing conferencing apps such as Zoom. In this case, we would just add functionality for converting ASL to speech. In non-virtual environments, ASL speakers would communicate with non-ASL users by simply opening a laptop in front of them in which VoiceOver would play. As they communicate in ASL, VoiceOver will recognize their gestures and automatically convert them to speech, so that even if the person in front of them doesn't understand ASL, they'll still be able to understand what they're saying. So our tech stack for this project was Python, MediaPipe, TensorFlow, OpenCV, and Google Cloud for text-to-speech. The initial algorithm we used when approaching the problem was hand border detection. So what we did was we used basic computer vision algorithms such as background detection and border detection to extract hand borders from images and then use them to train a CNN. However, we realized later that this method was not the best since it lost data about internal orientations of the hand, which is important for some complex ASL gestures. Another algorithm that we tried after that was canny edge detection. This extracts all the edges in a hand. However, this was still not very accurate because our data set perhaps was too small, or maybe because different people have different hand lines and the CNN could not successfully find a relationship between most of the hand edges. So our final approach was using MediaPipe, an open source library by Google. So what MediaPipe does is it simplifies a lot of the process for us by extracting details about landmarks in the hand images. So as you can see, it creates 21 landmarks for each hand and creates an XYZ coordinate for each XYZ coordinate for each landmark. So our final training method was that we isolated images using our existing method of background subtraction. Then we obtained hand landmarks for these images using MediaPipe, and then we fed these into our CNN. This was the best method as it extracted all the valuable data from a gesture and then used it to train the CNN. So for our CNN, we used Keras's sequential model with Adam optimization. Our loss function was categorical cross entropy, which is a good loss function to use for multi-class datasets. And we added more dropout layers than normal since ASL contains many gestures which look very similar. Our final prediction process takes user-generated images and isolates them using background subtraction. It then generates landmarks using MediaPipe and feeds these into our CNN. Our CNN generates text for us, which we then convert to speech using Google Cloud's text-to-speech API. However, we did not have enough time to create a dataset for this process since we already created a dataset for our initial algorithm. Our current model therefore uses our existing dataset, which was built for our initial training process. This achieves a reasonable final accuracy of 92.6%, but can be made much better using our final landmark model.
Moving on, we want to include support for the entire ASL dictionary and then add support for even more sign languages. And by using a better data set, we want to increase accuracy and precision. And at the end, create an app for better user interface. Thank you and goodbye.